Okay, let's move on to continuity equation for simple flow problem. So for this one, we have here a one-dimensional flow problem. This is a setup for one-dimensional flow problem. So let us consider this one as shown in the figure, in which a constant head is maintained across two layered soil for the flow of water. So the head difference between the top of soil layer number 1 and the bottom of soil layer number 2 is H1. So because the flow of water is only on the z direction. So for this one, meaning to say this is a one-dimensional flow for one-dimensional flow problem. So this is a continuity equation for simple flow problem. So we have here an inlet, a supply of water, and there is an outlet. So we have two layers of soil, soil 1 and soil 2. They have different hydraulic conductivity. At soil 1, that is K1, soil 2, that is K sub 2. So the head difference between the top soil and the bottom soil is equal to, that is equivalent to H1. So basically for this, you are given with the setup. Of course, we have a standpipe that is being connected to our container, our reservoir. So to compute for the calculation, you can apply this equations. So for our analysis, if we're going to consider the entire system, meaning to say the entire setup, the entire system of the continuity for this particular one-dimensional flow problem, for the total head, our total head is equal to H1 if we consider the entire system. So if we consider the entire system, our total head is H1. So meaning to say that is from the surface of the inlet towards the surface of the outlet. So that is our total head, which is H1. So the total length of the soil is H1 plus H2. This is the length of soil 1 plus the length of soil 2. And our I, hydraulic gradient, basically is equal to head difference H1 all over the length of the soil, which is H1 plus H2. And since this is a normal flow, this is only one direction of the flow of water, which is along z direction, and that is what we call a normal flow. This is the formula that you're going to use to compute for the equivalent K. So this is the formula for a normal flow as presented a while ago. So then you can compute now for the entire system the total flow, small letter q, that is K equivalent that we have computed times I, this is our I, times the area of the soil sample. So this is considering the entire system. If we're going to consider at point A, so at point A, our head H is equal to H2. So this one is our, this is our point A. So we have a piezometer attached to that. So this is the water surface. So from this water surface towards the water surface of the inlet, that is H2. So meaning to say, if you are considering point A, our head here is equal to H2. And our length, of course, of the soil is equivalent to y sub 1, because point A is from the surface of soil 1 towards this point. This is the surface of soil 1 towards this point A, that is y sub 1. So this is the length of the soil. So that is the length of the soil is y sub 1. And basically our hydraulic gradient is equal to the head all over the length of the soil. So that is H2 all over y sub 1. And permeability. So permeability for this, y it's equal to K sub 1. Since your point A is at soil 1. So soil 1, the permeability coefficient for soil 1 is K sub 1. So meaning to say the water will pass only one soil, one layer. So it will only pass through soil 1. And point A is at soil 1. So meaning to say our hydraulic conductivity at point A, if we consider point A, is the hydraulic conductivity of soil 1. Since our point A is located on soil 1 having a hydraulic conductivity of K sub 1. So which means that the water will pass only through soil 1 as it moves out at point A. So meaning to say our hydraulic conductivity at point A is equal to K sub 1. So our flow, which is Q sub A, the flow at point A is equal to K sub 1 times I times A. So we have our K, which is K sub 1, substitute I. We have identified that a while ago, which is H2 over Y sub 1 times A, which is the area of the soil sample. And continue the equation, basically the flow of water at point A is equal to the flow of water for the entire system, which has been noted by Q. Now, if we move on to point B, this is our point B, this is point B. So our point B, the head here is, point B is at soil 2. So there is a standpipe connected. So this is the water level surface. So basically, our head is equal to H3. So this is point B, you have a standpipe, this is the surface level of the water on the standpipe connected to point B. So this is from this surface towards the inlet surface, so that is H of 3. So meaning to say our head at point B is H of 3. For the length of the soil, that will be equivalent to the length of the soil at point B. So the length of the soil at point B would be equivalent to, this is point B. So meaning to say the water will pass from soil 1 towards soil 2 towards point B. So from point B towards soil 2, the level is the surface of soil 2, that is Y sub 2. From this surface towards this surface of soil 1, that is H1. So meaning to say our length of the soil at point B is equal to Y sub 2 plus H of 1. And the hydraulic conductivity would be equivalent to, of course, head H of 3 all over the length of the soil, which is H1 plus Y sub 2. And permeability coefficient. For the permeability coefficient at point B, this is point B. So meaning to say our water will pass from soil 1 towards soil 2 as it will move out towards point B. So meaning to say our hydraulic conductivity will be an equivalent hydraulic conductivity since the water will pass through layers as it will move out towards point B. So you're going to compute for the hydraulic conductivity. So that will be a normal flow. So you're going to use this equation to compute for the equivalent hydraulic conductivity since the water will pass through layers as it moves out towards point B. So you're going to use this equation. So that would be the height of the soil all over K equivalent. The height of the soil, of course, is H1 plus Y sub 2 all over K equivalent is equal to H1, soil 1, H1, the height of soil 1 all over hydraulic conductivity of soil 1 plus Y sub 2, the height from the soil layer, so surface layer of soil 2 towards point B, that is Y sub 2 all over. Since point B is at soil 2, so all over the hydraulic conductivity of soil 2. So this is now our permeability coefficient for the equivalent hydraulic conductivity. So flow at point B would be equal to K equivalent that we are going to compute times I, this is our I, multiplied to the area of the soil sample. And then for the continuity equation, basically, Q sub B is equal to Q sub A is equal to Q. Meaning to say continuity equation, whatever goes out on a certain point will be the same all throughout on other points. So that is Q sub B is equal to Q sub A is equal to Q. Then we have here hydraulics of well. So basically, hydraulic of well, to understand the process in effect when one or more well are pumping from on aquifer. This is, for instance, consider the analysis of drawdown due to pumping with time and distance. So the importance of hydraulic wells is that groundwater withdrawal from aquifer is important to meet water demand. Of course, we know that aquifer is an underground layer of permeable rock, sediment, or soil that yields water. So underground water constitutes an important source of water supply, which is very true because our underground water, it is a supply of water in some areas. So the stratum of soil in which the water is present is known as an aquifer. On the basis of their hydraulic characteristic, wells are divided into two categories. We have the gravity or water table well and the artesian or pressure well. So if the pressure at the surface of the surrounding underground water is atmospheric, the well is a gravity type. If this pressure is above atmospheric, because an impervious soil stratum overlies the aquifer, well is artesian. So basically, this is an illustration for a gravity well, and this is our artesian well. So from there, you can have your when you try to pump, of course, when you try to pump a well, there will be a drawdown, meaning to say the water surface well goes down. So that distance from the original water surface towards this line, towards this curve, that is our drawdown. And of course, this conical formation as you pump the well is what we call cone of depression. So if we're going to, for this gravity well, of course, of course, we have here your piezometers that is being installed, having a height of H1 and H2, and the distance from the center of this towards the H1 is R sub 1, and towards this H sub 2 is R sub 2. So if you're going to compute for the discharge for this gravity well, so you're going to have this equation. And for the artesian well, this is the setup for an artesian well. There is a confined aquifer having a thickness of T. And similarly, of course, there will be a drawdown, a decrease on the height of the water due to pumping. And this conical formation is what we call the cone of depression. So if you're going to compute for the discharge using this for this artesian well, you're going to have this equation. Of course, 2 pi k times T times H sub 2 minus H1 all over ln of R2 all over R sub 1. So you simply have to identify your parameters H2, H1, R sub 2, and R sub 1. And of course, your K, hydraulic conductivity, and your T, the thickness of the confined aquifer. And then you can compute now for the discharge for this artesian well.